Fischer-Tropsch synthesis as an alternative route for converting syngas derived from coal and natural gas to transportation fuels and other chemicals. Now it has attracted much interest in recent years. Due to the high FTS and water gas shift activity, iron-based catalyst is preferred catalyst for FTS using low hydrogen to CO ratio syngas from coal gasification or CO2 reforming of natural gas. In order to improve the catalytic performance of iron-based catalysts, researchers have studied the effects of some metal promoters, especially potassium, copper, and other transition metal oxides, as well as different supports. For example, potassium addition can restrain the hydrogenation ability, suppress the formation of methane, enhance the selectivities of olefins and high molecular weight products, and facilitate the water gas shift reaction. The performance of cobalt catalyst is not very sensitive to the addition of promoters like iron-based catalyst. In present study, we have synthesized precipitated iron catalyst using cerium, magnesium, potassium and copper as promoters or support. Up till now, major companies already using already using some catalyst is given for the Fischer-Tropsch synthesis is given in this table. Energy International is using partial oxidation. They are preparing syngas using partial oxidation with oxygen, using slurry reactor and using cobalt catalyst. Exxon company is using catalytic partial oxidation by oxygen in the slurry reactor and using CO as a catalyst. Rentec partial oxidation with oxygen, steam reforming and autothermal reforming in the slurry-based slurry reactor using iron-based catalyst. Sasol is using partial oxidation with oxygen, steam reforming, coal gasification, and they are using slurry as well as fluidized bed reactor and using both iron as well as cobalt catalyst, cobalt-based catalyst. Shell is they are preparing synthesis gas using partial oxidation with oxygen in the fixed bed reactor using cobalt-based catalyst. And Centralium is using autothermal reforming with air for the synthesis of syngas in the fixed bed reactor and cobalt as a catalyst. In the present study, we have prepared iron-based catalyst by two different methods. One is synthesis of precipitated iron was prepared using concentrated ammonia. We have added concentrated ammonia in magnesium, cerium and copper nitrates containing in iron nitrate solution and then precipitated the whole metals using ammonia and then filtration, washing, dry and calcination at high temperature. After calcination, the catalyst was impregnated with potassium and copper using potassium carbonate and copper nitrate respectively and calcined at 400 degrees for 4 hours. Second method that used for the precipitation is using ammonium carbonate as the precipitating agent. In the solution containing magnesium and iron, we have added ammonium carbonate in a water kept at 80 degrees temperature, then precipitated with the iron and magnesium as carbonates, and then filtered, washed, dried and calcined at 350 degrees. And again this sample was impregnated later on with 2% potassium and 2% copper, atomic weight percent, using carbonate and nitrate of the metal respectively. So the catalyst which we use in the present study, we prepared actually 3 types of catalyst. First is iron, magnesium, copper, potassium and cerium. In this catalyst actually we will use magnesium, copper and magnesium, copper and iron nitrates for the precipitation first, and then impregnated with potassium and impregnated with potassium. And Syria also we used as a support, but it was prepared during precipitation only. Secondly, this same catalyst we again impregnated with copper nitrate. The second catalyst we prepared is magnesium promoted precipitated iron catalyst, electron impregnated with copper and potassium. And third is iron precipitated catalyst, electron impregnated with potassium and magnesium. We have carried out the evaluation of the catalyst for the pore structure using nitrogen adsorption isotherms, using AutoSorb 1 instrument. The isotherms were used to calculate the bed surface area, total pore volume, and divergent pore diameter. The phase identification of iron in the catalyst before and after the reaction was identified by XRD patterns. Also, particle size of the active species was evaluated using Scherer equation from their most intense peak from the XRD pattern. The reduction of iron oxides in the sample was evaluated by temperature program reduction method. This is the XRD of the three catalysts we prepared. So all the three catalysts, they show typical hematite Fe2O3 phase for all the samples. This sample it shows the comparison of the fresh magnesium promoted precipitated iron catalyst having ratio magnesium to iron 0.1 by atomic ratio, and second is the used catalyst, same used catalyst after the reaction at 250 degrees for 20 to 20 bar for 25 hours. It is seen that iron carbide, it is CFE 2.5 around 43 here. It is marked by this symbol O, and magnetite it is marked by the sign plus. All these are magnetite phases, and this is a phase of iron carbide, which is carbon Fe 2.5. And actually, it is postulated that this iron carbide phase, it is the active phase for the Fischer-Tropsch reaction for the iron catalyst, and it is also responsible for the WGS reaction. So, the XRD shows that as the reduction of the catalyst proceeded, iron oxide, this is the iron oxide which is present in the form of Fe2O3. Then as the reduction proceeded, it was transformed from Fe2O3 to Fe3O4. So all the peaks which are marked by the sign plus, it is Fe3O4, which is which is reduced from Fe2O3 to Fe3O4, and then later on it should show to alpha Fe or iron carbide. Alpha Fe could not be observed in our reduced catalyst because metallic iron was fairly reactive to carbon dissociated from carbon monoxide. These are the this table shows the active phases and the particle sizes of the spent catalyst. So for the catalyst, which is first catalyst which we have prepared, magnesium, copper, potassium and ceria. In this case, magnesia and ceria, totally it is around 10%. And in all the catalysts, copper is around 1% and potassium is around 2% by atomic weight. Then in this particular catalyst, the phases found after the reduction were Fe3O4 and one more Fe carbide phase it was found. But then this catalyst, when it was again impregnated with copper, then Fe3O4 and carbon Fe2 phase was observed. These results suggest that particular amount, concentration of copper is needed to form the active phase, which is carbon Fe2.5. In this particular sample, iron carbide phase was formed, but it was not carbon Fe2.5, but it was some iron carbide phase which was not active for the Ft reaction. And that is why this catalyst has not shown the reaction. Explain the preview. Then this is a promoted iron catalyst. It has shown Fe3O4 and carbon Fe2.5 as active phases with the particle sizes 13.5, 9.5, and the peak ratio of these two. This was 0.588, and for only a precipitated iron catalyst, it was 6.3 to 5.25, and ratio was 2.4. So this is a XRD pattern of the spent catalyst for the first sample, copper, magnesium, and ceria. Then this is precipitated iron catalyst, and this is magnesium promoted iron catalyst. So in this XRD, we can observe that the average particle sizes of the iron oxide and the iron carbide in different catalysts were estimated from this most intense peak to theta 35.5 and 43.1. With magnesium, the particle size of the active phases was found to increase. With addition of magnesium, the degree of reduction was found to decrease. So this table shows. This is the XRD figure. It shows the comparison of the XRD of the used precipitated iron catalyst using magnesium promoted precipitated iron catalyst with FeMg CuSO3 catalyst after reduction in syngas at different temperatures. So this catalyst is the spent catalyst after the Ft reaction, and this is the first catalyst which we prepared here. FeMg potassium Cu. Actually, I have written a question mark here because copper we had taken during the precipitation of the catalyst, but we don't know whether it is there or not because the results have shown that copper was not present or may not be at particular level which we were desired. So that is why this XRD shows that this is a catalyst which was reduced in the syngases 270, 400 and 500. So this iron carbide phase, it can be clearly seen that it is shifted from this particular peak. This has shifted to the right side to the higher theta to theta value, and that is the reason why this catalyst has not shown the reaction, because whatever iron carbide phase has formed, it was not active for Ft reaction, and that is why when this catalyst has not shown any activity, again we have loaded, we have impregnated this catalyst with copper, and later on this catalyst has shown activity. This explains again, use the FeMg copper catalyst shows the active carbon Fe carbide phase at 43.5 here. Magnesium promoted iron catalyst and series supported does not show the reaction when catalyst was reduced in the same gas as 270, 400 as well as 270. And here, even if the active phase was found iron carbide, the concentration of the active phase was not enough to carry out the reaction. That is why it has not shown the reaction. And because concentration was less, because there was no enough amount of copper present in this sample, and therefore no active phase, that is carbon Fe, was formed in this particular catalyst. Then higher temperature, this peak was shifted to the it was shifted to higher to theta value because of the formation of iron carbide, which is not active in the Ft reaction. The result suggests that the lack of sufficient copper in FeMgCu, potassium ceria, lead to the formation of inactive iron carbide phase in the reduced catalyst. Then this This is we have compared this fresh catalyst which we have prepared this FENG supported Syria catalyst with this all different temperature reduced at different temperature, and here again it is seen that the peaks means Fe3, Fe2O3 peak and iron carbide peaks they have shown the shift. This is the nitrogen absorption curve. The bed surface area is around 64 for this particular sample because here Syria and magnesia they act as a structural promoter and hence bed surface area is more. Then this copper impregnated has shown 57.19 and magnesium promoted has shown 28.89 and so on. The TPS study shows that this curve number 1 is precipitated iron catalyst, then curve number 2 is magnesium promoted precipitated iron catalyst. Due to magnesium, the reduction temperature of the catalyst is decreased. Then here this is the catalyst which is iron magnesium supported on Syria catalyst, but it has no copper in it. Even if you are taken during synthesis, the copper has leached out during the synthesis, and therefore the reduction temperature was a high temperature when this catalyst was again impregnated with copper. It has shown the reduction temperature to reduction at low temperature. So the first peak around 200 to 300 shows Fe2O3 to Fe3O4 and CO to CO reduction here. Then the second peak 300 to 400 is due to Fe3O4 to FeO. And the third one is at this wider peak is due to FeO to Fe, and the peak is wider because it takes long time or it is a slow process. That is reduction of FeO to FeO to Fe is a slow process, and hence we are getting a broad peak. We have carried out the reaction in the fixed bed reactor, and we got the result. We got suggests that the addition of magnesium promotes the formation of hydrocarbon to lower carbon number compared to the non-promoted iron catalyst, and they form only solid waxes. It is around 1.2%. The conclusion is that below level of the active phase of carbon Fe2.5, reaction may not proceed. Sufficient copper is essential for the formation of active, that is carbon Fe2.5 phase during the reduction of precipitated iron catalyst. Magnesium reduces the reduction temperature of the precipitated iron catalyst. FTS results suggest that addition of magnesium promotes the formation of hydrocarbon to lower carbon number compared to the non-promoted iron catalyst. So the next is that since magnesium promotes the activity of the FTS catalyst towards the lower carbon number hydrocarbon, so we are going to standardize the amount of magnesium to Fe so that we can get the product which will be more towards in the middle distillate or gasoline range.